So, good morning, everyone. It's 9:30, so I will officially open the session. Welcome to the second day of this international workshop on CO2 capture and utilization. My name is Fernanda Neira D'Angelo. I'm from TUE, and well, it's a pleasure for me to be the chair of this first session of today. The program, as you see on the screen, is as follows. So the first half an hour, we will start with a brief introduction of the projects that are supporting this workshop. And later at 10, we will move on to our plenary session. There is a terrible echo. Not sure how to avoid it, to be honest. I could do something. Can someone comment if the echo is gone now?
We don't see we cannot hear the echo. It's fine for us.
Okay. So, well, I will continue then like this. I'm sorry for the ones, yeah. So at 10, we will move on to the plenary session by Dr. Bake from Northern Lights. So, well, let me, and also I should remind you that all these meetings are recorded. So later the videos will be made available on the website. So let me share the first set of slides. Okay, is it visible for all of you?
Yes.
Okay, perfect. So yeah, so the first part of the program today is the introduction of the projects. As you all know, there are a number of projects, European projects that have sponsored and support this workshop. The entire list is visible on the screen. So we have 11 projects, and I will give the word to the coordinators of these projects so that they can briefly introduce their projects to you. Please, to the attendees, if you have any questions, write them on the chat, and I will, at the end, if there is time, give some space for answering questions. So the first presentation is by José Luis Viviente from the project of Member. Sorry, here I jumped too quick. There is a slide with the names of the projects, but also the websites for your interest to check later if you want to check. So the first project is by José Luis Viviente. So José Luis, if you can unmute yourself and go ahead in a couple of minutes.
Thank you, Fernanda. I will present in a few words Member. That's a project that aims to reduce the cost of carbon dioxide capture technologies. And the idea was...
José Luis, sorry
yes.
that I interrupt already. If it is possible for you to open the camera, that would be nice.
Okay, yes.
If it is an option. Thank you.
Fine. I'm here. Hi. The idea is to reduce, we work in 3 different lines with 2 different concepts. One is the mixed matrix hollow fibers developed to CO2 capture in power plants in pre and post combustion application. And the second one is using membranes combined with sorption enhanced reforming to develop a new concept that we call membrane-assisted sorption enhanced reforming, where we produce hydrogen with integrated CO2 capture. And the idea of the project is to increase the manufacturing level of all the materials and membranes we have to develop and demonstrate their validation in the capture technology at TRL6. So we cover the whole chain from developing mixed metal organic frameworks, having polymers, developing has amount of mixed matrix hollow fibers. We go to the 100, maybe 50 centimeter long hollow fibers to 10,000 meters long amount of hollow fibers. And also we go for sorbent to 200 kilograms production of catalysts, also to the 50, 60 kilograms production. Also membranes will increase the production of per batch as well. So the idea is to, besides to demonstrate that these new concepts are valid for the TRL6, to be able to increase the manufacturing capacity in the value chain, so we can further increase the TRL for higher flux or CO2 capture amounts. And the target we have is to at least capture 90% of the CO2 in all the three applications, and decrease the cost to lower than 40,000 euros per ton or 30,000 euros per ton. So we are around 17 partners with 11 industries and SMEs companies. So it's a very industry-oriented project. So if you want to see more information, you can visit the website. Thank you.
Thank you, José Luis. Then I will give the word to Adolfo Benedito from the group, the project Carmo. Adolfo, we don't hear you, but I'm not sure. Is Adolfo on the, I don't see him on the presenters. So I will move on to the next one, and then when Adolfo comes back or someone can present this project, we can return to this. So the next one in line would be Oana David from the project BioCommand.
Good morning, everybody. I'm working at Tecnalia. We coordinate project BioCommand. Here, the aim is to develop membranes, competitive membranes, starting from bio-based building blocks. We aim at 3 applications, all of them related to carbon dioxide separation. So we aim at carbon dioxide separation from biogas, from natural gas, and from post-combustion gases. There's a lot of work in the chemical synthesis of bio-based polymers. The chemistry will be based on block copolymers like polyether block amide polymers. So you can see at the left, the core material will be synthesized by coordination between University of Maastricht, Arkema, Big4 Plastics, and also a group from Tecnalia, the Chemical Sustainability Group. And then my group, membrane group with Polymem, we will scale up these polymers into membranes, and we will scale up the membranes. And then there are many other supporting activities like testing and life cycle analysis, recyclability and plastic footprint, and process industrial requirements that are supported by Quantis, DMT, and University of Eindhoven. So thank you very much.
Thank you, Anna, very much. The next one would be Kamel McLuffy from C2 Fuel.
Hello, everyone. So my name is Kamel McLuffy. I'm from NG, and I'm coordinating the C2 Fuel project, which aim to demonstrate the potential of e-fuels, namely dimethyl ether and formic acid, in the industrial ecosystem of Dunkirk. So in Dunkirk, we have an integrated steelmaking factory, basically a steel factory, belonging to ArcelorMittal, connected to CCGT belonging to ENGIE. And so this CCGT consumes the blast furnace gas emitted from the steel factory. It contains a lot of CO2. So the idea is to use the large potential of renewables in the area to produce green hydrogen and combine this CO2 to produce e-fuel. And that could be used later on in the Dunkirk harbor, which is just in the vicinity. So there's a lot of intensified technology which are developed in the frame of Cetofuel. First, on the production aspect, first intensified technology for the electrolysis. High temperature electrolyzer are developed and demonstrated at Dunkirk on the site of the power plant. And then there's also intensified reactors. For DME production, we developed membrane reactors and also innovative spinning disk reactors for the production of formic acid. So there will be a demonstration of the production of DME on the site of the power plant, and it is ongoing. There's also alternative way to produce e-fuels, and for example, direct CO2 electroconversion into formic acid. On the utilization aspect, we have two main developments driven by large companies, Volkswagen and SMEs Dance. First of all, a new DME engine are developed in the frame of the project, but also, very interestingly, a new kind of e-fuel genset using formic acid to feed a PEM fuel cell, and that will be used for cold ironing in the Dunkirk harbor, which is one of the most important in Europe. So the Cetofuel project has, I would say, 11 partners, as mentioned downstream, and has been funded by the European Commission. So feel free to contact me, or let's have a look on the Cetofuel web page. Thank you.
Thank you, Kamel. I now would like to give the word to Richard Hain from Cosmos.
Thank you very much. My name is Richard Hain. I'm a senior researcher at SINTEF, and I am the communication and dissemination manager for the Cosmos project. The goal of the Cosmos project is to overcome equilibrium limited CO2 conversion yields by exploiting Le Chatelier's principle, and then combine the two reactions of CO2 to methanol and then methanol to hydrocarbons with one bifunctional catalyst in one reactor. We are targeting C3 products, propane and propene, and the aim of the project is also to try to tailor the product yields for either propane or propene, depending on the needs and the infrastructure and the amount of hydrogen that is available at each specific CO2 emission site. We have two CO2 emitters on the project, Tata Steel and Tupros, so we have a range of different CO2 hydrogen gas mixtures that we can use to explore the catalysts. We have the coordinator, Uni Olsby, is presenting on the catalyst development today at 12:30, so I encourage you all to attend her presentation. You'll find much more about the status of the catalyst development in her talk. And Marta Fernandez from Tata Steel has a poster on the LCATA analysis in the project. Thank you very much.
Thank you, Richard. So the next one will be Jose Maria Serra from IWCCU. One moment. Yeah.
Okay. Thank you. So this is a project we call ICOCO2, but that depends on who reads it out. So our project targets the intensified conversion of industrial CO2 into hydrocarbons. So the main target is jet fuels, although we have intermediate milestones on methanation and olefin production. We target to reach TRL 5, and the technology is based on the combination of multifunctional catalysts that enable the first CO2 hydrogenation into C1 species, and then the oligomerization into the target molecules by using a molecular sieve with zeolites with shape selectivity. The electrochemical cell is based on protonic ceramic conductors that show combined proton conductivity, so injection of protons from the steam, and extraction of water from the reaction chamber, where we are producing very large amounts of water during the CO2 hydrogenation. This is very well known, and this approach also enables in another way to to shift the equilibrium and reach higher productivities of the hydrocarbons. So the consortium includes leading companies on energy and manufacturing that produce CO2, like Shell, ArcelorMittal, Cemex, and ERA Group. That is a group managing waste, and in south of Europe. And then we have Costec as the membrane technology provider and also developer. And we have groups on protonic conductors, that is CSIC, SINTEF, University of Kyushu and Oslo University, and UPV. And we have finally for social perception and different surveys, we have RBTH. And that's everything from my side. Thank you for your attention.
Thank you. So the next one would be Vesna Midelko from Vito to present about CO2 focus.
Hi, good morning, everyone. I'm a coordinator of CO2 Focus, and CO2 Focus has other 12 partners, which are coming from the countries which are mapped there. We have a nice blend of RTOs, research organizations, and mostly SMEs and industry, which amount to more than 60% of our consortium. That's us in a nutshell. But other than that, the main concept, the main aim of CO2 Focus is reactor concept and process design for CO2 conversion to DME. And more precisely, the concept concerns the development of direct step CO2 hydrogenation technology to recycle industrial CO2 into DME, which the CO2 we are going to source from our industrial facilities at petchem sites. That's a petrochemical industry, which has abundant. It's just one of the basically large CO2 emitters, which we're trying to demonstrate at the end, at the last leg of our project. However, in the meantime, since we started up to now, it's month 18, we've been working on the development of the reactor concept itself by 3D printing and optimization. The reactor concept relies on the multi-channel, multi-tubular reactor system, which has highly favorable heat and mass transfer properties, then enables also low pressure drop, which all aims for kind of cost-effective, energy-efficient DME production. On top of that, this is very important, the multi-tubular system for the scalability that brings advantage to scalability of the reactor. On other sides, just for hydrogen supply, we are working on developing and manufacture of about 3 kilowatt solid oxide electrolyzer, just optimizing the stack size and its operation so it could supply hydrogen for DME production. As said, verification of all these process parameters, some of them are just quickly summarized at the bottom of the slide, but the verification will come at the very end of the project, where we are going to have this kind of modular, flexible unit installed at CO2 point source. Yeah, that should be enough.
Yeah, it is. Thank you very much. So the next one will be Harun Magedeh. I'm really sorry for this pronunciation. I'm sorry, there are some animations in this slide. I will just put them on, if you don't mind. Yeah. So on the project C4E. Is Harun available on the chat? As a speaker? No, I don't see. Okay, so the same as before, I will move on to the next one, which is Ina Kim. Sorry, this was, no. Ina Kim from Realize. Is Ina?
Yes, sir.
Okay.
Thank you. Good morning. My name is Inna Kim. I'm research scientist at SINTEF and coordinating Realize project. Our project is focused on validation and demonstration of CO2 capture technology based on solvent. And we focus, even though solvent technology is in use for decades, is some special thing with the post-combustion capture and impurities in the flue gases that we have make some challenges that were not addressed earlier. First of all, it's presence of oxygen in the flue gas, in the feed gas, that is degrading our solvents and can increase emissions due to it. So we are focusing on demonstrate our solvent that was developed in an earlier EU project has a higher stability and less emissions. That's what we plan to demonstrate in our project, and focus on solvent degradation and emission measurements here. Then the results will be implemented in models and technologies for solvent management, and solvent and CO2 capture will be projected for full scale and techno-economic assessment done for that for different refineries. We have also an important activity on societal study, and there was a presentation yesterday on it, and I will present our project later today. We are 14 partners in Europe, 2 partners in China, and 1 partner in South Korea recently joined the project. Thank you.
Thank you very much, Ina. Now, yes, Gianpaolo Manzolini for Converge.
Yes, I'm here.
Yes.
Hello, everyone. Thank you for. Oh, this is not the updated slide. Anyway,
These are not the slides?
Yeah, it was supposed to be another slide where all the partners and the acknowledgements were included. Nevertheless, the Converge project is an innovative project with a low TRL. So we start from TRL 3, and we hope to take the technology to TRL 5 by the end of the project. And the concept is about developing new process and components for converting secondary biomass into biomethanol with higher efficiency and lower cost respect to the state of the art. Another relevant outcome of the process is that we expect to produce negative CO2 emissions that can be also exploited in terms of economic point of view. The technology consists of 4 main concepts or processes. The first one is about a catalytic cracking reactor, which converts tar into BTX. Then we have the sorption enhanced reforming, which due to the simultaneous conversion of methane and separation of CO2 improves the efficiency compared to the state of the art. Then the hydrogen is compressed through the electrochemical hydrogen compression. And finally, the methanol conversion is enhanced by membrane inside the reactor itself. The project is now halfway through, so we're around half of the project. And now the technology is designed, and we expect in the next year to be manufactured the different prototypes and be demonstrated in 2022. Thank you very much.
Thank you very much. I'm sorry for the slide. I may have taken the wrong one. I don't know. Then the next one would be, and the final one is Michael Zampas from Kero Green. Is Michael in the chat? Not really. Anyone from Kero Green instead? Also not. So with this, we finish with the.
There is people from Kero Green in the chat box that mentioned France and Stefan Felsel, sorry.
Okay.
And he has to be made presenters.
Alessandro, can you look at it? Who is it?
Stefan Felsel.
I'm seeing someone else. No. Stefan, yeah, here I see him.
I've done. Stefan is here. Good morning. Can you hear me?
Yes, we can.
Good. Thank you very much. So yeah, again,
right now we have, I'm sorry that I interrupt. Right now we are looking at the camera of Adelbert Hood. Maybe, hi, nice to meet you. Can you switch off the camera? Yeah, we don't hear you, unfortunately. And then we could switch on the camera of Stefan instead. Thanks.
There we are. Okay. Can you hear and see me? Okay. Was this a yes or no?
Yes.
Yeah, it is.
Okay, sorry. Okay, yes. Yeah, good morning, everyone. Apparently, my colleagues have, again, some technical issues with logging in this morning. So I will be taking over from Albert Goede, who is the coordinator from different side for the Carroll Green project. And this is a project, if you like, about the electrification of producing chemical feedstock, or in this case, specifically a sustainable aviation fuel, kerosene. As you can see on the top left, there are a couple of modules that we try to integrate in this project. It starts with an electrical gas discharge, plasma, which uses CO2 in order to generate a mixture of CO2, CO, and oxygen. The oxygen needs to be filtered out, for which we will be using a solid oxide electrolysis module. Later on, the CO is purified and then goes into a water gas shift and Fischer-Tropsch reaction chain. And finally, with some additional hydrocracking, the kerosene is produced. Now, to give you an idea about the TRL levels, this is 1 up to 3. So on the left-hand side, we are more on the earlier TRL levels, especially if it's about combining a plasma reactor with the oxygen separation and the separation by itself. And on the right-hand side, it's more on the higher TRL levels. And at the end of the day, we want to achieve TRL level 4. And we try to achieve also somehow 3 liters of kerosene produced per day in a container-sized unit, which will be then located at the Energy Lab 2.0 at the KIT campus in Germany. And as you can see, actually, each module that you can see on this graph is connected to one of the partners. So DIFFER is taking care of the plasma reactor. In a joint effort, the oxygen separator is manufactured, if you like, by Vito, Highgear, and DIFFER. The CO purifier is taken care of by Highgear, and as I mentioned, the Karlsruhe Institute of Technology in Germany provides the container where all the modules will be integrated, and is also taking care of the water gas shift and Fischer-Tropsch module together with Ineratec, another company from Germany. Project started 2018. By the end or by the beginning of next year, we hope to achieve our also project goal. And if I'm not fully mistaken, there is today at least 2 presentations also in the framework of this Carroll Green project by KIT and Highgear. And if there's any question, feel free to contact my colleagues or myself during the course of this day as well. Thank you very much.
Well, thank you very much to you too. Is there any general question that we can address within a couple of minutes? If so, please write it in the chat. Well, I don't see many questions, and I had a few, but in view of time, I think I will keep them for another moment. And I believe that there will be many presentations on these same projects in the coming session, so probably that will already answer them. So I want to thank all the speakers, and I want to move on now to our next part. Let me change the slide. One moment. Yeah. So I want to take a moment to announce the upcoming conference, World Conference on Sustainable Technologies. Do you see the? I hope it's okay. You see. So I want to announce the upcoming conference on sustainable technologies, which is exactly in 1 month from now. There are already very excellent speakers, as you see on the screen. And if you are participants of this workshop, you can have a discount. So for information about the discount and also about the conference, please look at the website that you see on the bottom. And now this brings me to the next part, which is our plenary session by Dr. Knut Bakke from Northern Lights. Again, if there are any questions, please write them on the chat and we will look at them later. I believe Dr. Bakke is already a presenter, correct? I saw him before.
I'm here anyway, so.
Okay, so please, the floor is yours. If you can already share your slides. I'll stop sharing.
I'm working on it, so I know. It's just a web version of Teams. It's a bit unfamiliar to me, but let me know if you can see my screen.
Not yet, no. Yeah, now yes.
All right. And I understand I have an hour. I'm not probably not going to.
Yes, there is an hour. So the conference, at 11, we will start with the poster session. So it would be nice if we have some time for discussion afterwards.
Yeah, no, I'm not going to use an hour, so hopefully we can have some good Q&A after the.
Okay, that's perfect.
After the
Thank
presentation. You. So yeah, thank you very much for allowing me to speak here. I'm going to speak of something that's probably a lot less technical and detailed than what I understand a few of the other topics. So you'll bear with me. This is a project in execution phase. As a collaboration between Equinor, Shell and Total. I intend to talk about what it is. I intend to talk about some of the elements, some of the issues around storage, importantly for us, whether there's a business opportunity in CCS, and some challenges, and then I'll sum up, and hopefully we can have some good questions. So Northern Lights is the name that we've selected on the transport and storage part of the CCS value chain in Norway, which is a collaboration between the Norwegian government and the industry, and in this case represented by Equinor, Shell and Total, and we aim to collect and store CO2 from industrial emitters around Europe. So if you can make those capture technologies cheap and available, we are there to collect CO2 and transport it and store it safely. So I'll get into that in a bit. So basically, our idea is to separate the source and the sink. What you see here is the traditional CCS model, where there is an industrial point source. It could be offshore or more conventionally onshore, with a one-to-one relationship between the source and the sink, where it's a massive project undertaken to capture, transport, and store CO2. Takes a lot of competence, a lot of capital, and it has proven difficult in the past to find good projects that can stand on their own feet in terms of economy, and that's a little bit of the challenge. So what we aim to do is to take the complexity away from the industrial sources by offering a service of collecting CO2, transporting it, and storing it in an underground reservoir for permanent storage. So the idea behind this is that oil and energy companies are competent and familiar with geology and the offshore work, while the industrial emitters can then focus on running their industry and learning how to capture CO2 from their particular industries. So we are part of something that was named by the Norwegian government as a longship, which is a direct translation from the ships that were used by the old Vikings when they traveled around Europe. So it's intended to be a start point for an industry where we have a value chain with CO2 capture. We had in the initial stages 2 industrial emitters, one from a cement factory and one from a waste incineration facility in Oslo. And we have a transport piece, which for us is in liquid pressurized form in ships. That has to do with the distance between the point source and the storage facility. So in the future, there may be other solutions with pipeline-based networks as well, and we don't really see that as a competition. We see all CCS as complementary at the moment. So this is the concept where we basically capture CO2 from industrial plants. We compress and temporarily store the CO2 in tanks. Our process conditions is typically 15 bar minus 26 degrees C. We transport it into a ship, and of course the Northern Lights scope of work is what's green on the screen now, and ships, an onshore facility and offshore storage. We take the CO2 compressed and transported by ship. We receive it at an onshore facility that will be located outside of Bergen on the west coast of Norway, where we receive and temporarily store the CO2 in the tanks that you see. We export it via an offshore pipeline and inject it in the reservoir some 2,500 meters below the seabed. And as you can see, the process is a batch operation when it comes to ship offloading. It's a continuous process when it comes to injection, and therefore the need for interim storage tanks. The Longship project, as it stands today, has funded the NOSEM facilities. And I can put up a pointer probably. NOSEM facilities, it's a cement factory located here south of Oslo, which is up here. They will start up CO2 capture in 2024. There's also partial funding from the waste incinerator facility up in Oslo, but they need to attract additional funding. So the FID for this one is sort of on hold until they can attract funding. Then we transport CO2 along a shipping route using purpose-built vessels. I'll get back to that. To the onshore facility here west of Bergen, an onshore facility being established, export into the offshore and injection to a subsea facility. So currently we're building a facility scope with capacity for 1.5 million tons per annum. We have 2 ships on order, and the volume from Norcem alone is 400,000 tons per annum. So by deduction, you can see that we're looking for more customers. More on that later. The CO2 capture at the Norcem facility is illustrated here. They aim to collect 400,000 tons per year, which is about 50% of their CO2 emission. The reason they're not capturing all is one of heat surplus. 50% can be captured using surplus heat in the process. So that's what they're aiming for. What you're looking at here, all the gray stuff is the existing cement factory. All the colored stuff is new scope with the capture facility here, delivered by Aker Carbon Capture. The blue are new buildings, and the CO2 will be captured and exported through to the storage tanks here, and finally offloaded on a commercial harbor called Grenlandhavn, where our ships will arrive and collect CO2 in the operations phase. So what is Northern Lights? I'll get into a bit more detail about what we are doing. First and foremost, we're looking at CO2 transport by ship. That is an existing trade today, with the food grade CO2 being exported by ships to breweries and greenhouses, etc., around Europe. One of the sources is from the fertilizer factory owned and operated by Yara, not too far from Norcem. And that's the sort of the starting point for our transport conditions. They typically transport in these conditions on smaller ships. So our step out is the size of the shipping. And we have basically taken a relatively standard LPG ship that we are familiar with in the oil and gas industry, which is the idea by using a standard ship is to not pay a lot of money for developing something brand new, but rather take off-the-shelf designs and modify. So we have a proven concept based on this food industry model. We basically developed the storage tanks in the ships, and we aim to copy paste buying more ships. Potentially we're going to make them a little bit bigger. It depends on the future market for transport and storage. And our delivery contract is about to be signed, so we'll start to work with the shipyard in the second quarter of this year. These ships will be run initially by LNG fuel. They will have power from shore when docked, and we are also looking at options for running them in the future by hydrogen or ammonia, in essence zero emission vessels in future versions of these ships. We do have a collaboration with a number of industry players in Europe, as you can see illustrated here, through what we call PCI under EU, Project of Common Interest. So it's open for EU funding for the transport bit. And all these dew points are industrial companies that we have collaboration with in this. And there are also a couple of storage projects that we also collaborate with. In theory, we plan to have the ability to exchange storage between these. That's on the drawing board at the moment. Yeah, and if you look at the onshore facility, I apologize for the language on top. It's a bit of English, but a bit of Norwegian. It means Northern Lights onshore facility in Øygarden, which is the name of the municipality where the facility will be located. You can see the location here. Bergen is here, and this is very close to Equinor's existing gas facility at Kolsnes, which is here, and the Sture oil terminal, which is here. And what you see here is an artist impression of how this facility will look in the first phase, with obviously dominant product jetty with industrial loading arms. So this is more than they do in the food grade industry, where they use hoses and a manual operation. We will use mechanical loading arms to make sure it's safe and efficient at the transfer point. The CO2 will then be loaded through pipeline into these storage tanks, and there will be a gas return in the system. So when we move CO2 here, the vapor space on top of these tanks will be moved back into the ship. So there's essentially a zero emission concept. Our calculations suggest that the whole value chain life cycle analysis, including CO2 emission from construction phase and operation phase, depending on stored volume, we're looking at single-digit CO2 percentage CO2 loss from the value chain. So typically 2 to 4% of the CO2 stored is lost in the transport, in case you have that question. This is the current state of affairs. The facility I just showed you, we have an administration building, we have a workshop and an electrical substation to run the pumps who are located here, that will pull CO2 from the storage tanks and inject it into a landfall tunnel, which will be located in this area. At the bottom here, you see some pictures of the state of affairs. We're building a site office. It's actually finished, so the picture is a little bit dated, and we're currently working to blast and excavate this area. So the hill you're looking at here is somewhere here in the illustration. So currently we're moving mass out of the area in order to prepare it. Some of our contractors are listed below. The idea is that we will take a mass from here and fill out the little bay up here and create even more space for the industrial area. This is an industrial park pre-existing, so it's got a lot of facilities already. Pipeline and subsea facilities, we already installed this template that you're looking at here in 2019 when we drilled our confirmation well. You see a picture here of this yellow bit at the sea bottom with the fish and our name on it. We drilled a confirmation well in 2020 before we took final investment decision in order to prove up the storage concept in this area. I'll get back to that. We have started fabrication of a control umbilical, power fiber optics, We are starting with engineering and modification at what's called Oseberg, which is an oil and gas facility in near to our injection well. We have decided to pull the controls back to that platform in order to save money on the umbilical and control cable cost. We have started to design the pipelay, and again, a few of our contractors you can see here. Here is a rather busy illustration. It's intended to show you the location of the onshore with the pipe route going out here into the area where this well that I just talked about, it's called EOS, is located here. The offshore installation for control cable is located here. And we also are planning a contingent well in this area. All these lines are trawling patterns from bottom trawling activity in 2018, and it shows that it's a fairly busy area. So one of our very important parts of design and installation is obviously not to conflict with fisheries. That means we need to have over-trawlable facilities, and we need to work coexist with the fishing industry rather than fighting them, which is something that we obviously have been doing for a long time in the oil and gas industry. For illustration, up here is the Troll gas field operated by Equinor with the pipelines back to Mongstad and the Kolsnes gas facility here. The Troll is both an oil and gas producer. Now to the storage concept. So I've tried to illustrate it. I'm not a subsurface skilled person, so this is a layman's description of the scope. But what you're looking at here is the well that we already drilled, which we will get back to later and complete for injection. And we have modeled the purple part here is the expected extent of the CO2 modeled with an assumption of a certain volume injected that we have committed to in what we call phase one of this project. And we are injecting into what we call a sloping aquifer. So these are sandstone formations with water, not to be confused with oil and gas structures. This is one without oil and gas in it, and it's only used for storage, meaning we are not looking for EOR opportunities or things of a similar nature. This is purely for addressing the climate issue. But you can see the reservoir is slightly sloping. It's exaggerated in the figure. It slopes by about 2 degrees. So over a long time, we expect the CO2 to migrate upwards here, contained by what we call the primary seal, which is indicated here. We also have a few other caprock structures working as secondary seals. This is about 2,400 meters behind the seabed, and the concept is obviously to inject here, learn more, and possibly inject much higher volumes than what we've indicated here. This is what we've committed to at the moment. So you see the well here, and it's vicinity of the Troll oil and gas field, which is actually up here. So one of our primary objectives is, of course, to ensure for everybody that we're not moving CO2 into a producing oil and gas field we're fairly confident we will not do that. And if you see here, 2049, the current plan for decommissioning of the Troll gas field is in the same time frame. So we're pretty confident that we can accomplish this. What we're looking at here at top is the trapping mechanisms in between the sand grains on the microscopic level. This illustration is to illustrate that we're actually talking about a number of trapping mechanisms. Initially, it's a structural and stratigraphic trapping, while as we move to the right in this figure, more and more of the CO2 would be trapped residual by capillary forces in the porous media. Eventually, we'll move to solubility trapping, meaning it dissolves in the water that's there. And you can see the time scale here, logarithmic, means that the contribution over time is moving from left to right, making the storage, let's say, more and more safe, less and less potent as we move up in time. And this reservoir is hydrostatic, meaning there are no driving forces for the CO2 to go elsewhere other than the density difference between CO2 and water, which are moderate at those conditions. So I'm going to talk a little bit about the storage experience. So this is industrial experience from Norway, meaning we are not doing this for the first time. Equinor has injected from Sleipner since 1996 and from Snøhvit from 2008. Both of those are gas-producing fields with excess CO2 that, driven by this local CO2 tax in Norway, has been commercial CCS projects on their own right. And we've stored nearly 20 million in Sleipner. We have a publicly available data set for the storage, so we're trying to be very transparent on the storage bit there. Snøhvit have injected a bit less, but more recent, and that's a subsea facility which is similar to what we have in terms of the injection technology and the wells used up there. So it's not something new, and of course Shell and Total has experience as well with Shell's most dominant project at the moment is the onshore Quest project in Canada. Also partner with Gorgon with the Chevron on Gorgon on the LNG facility in Australia. So there's quite a bit of industrial experience gained already. And of course, one of the more important questions that we are asked is how do we know that the CO2 stays in the ground? And we're doing that by a number of measures. The most important one is by seismic monitoring, and the example here is before and after seismic footprints from Sleipner. And the one to the right there is of course the subtraction of one from the other, showing the extent of the CO2 plume. So this is one of a number of monitoring technologies that we use to ensure that storage is safe and under control. So that's a bit of the technology. I'll end up with a few other, let's say, less technical issues. One, of course, is very important for a commercial company like Equinor, Shell and Total. Is there a business opportunity? We're not a charity, obviously, so in order to make it sustainable, it needs to be seen as a future business. And I just thought I'd bring this one along. What you see on the left, I don't need to explain, I think, but on the right there is the ETS trading price for CO2 in euros, and you can see it's been steadily, or maybe not so steadily, but it's certainly been increasing, and it's hovering around 40 euros per ton at the moment, which is a big enabler for any carbon capture and storage aspiration, is to get a balance between the costs, which are currently too high, and the cost of emitting CO2. So if we can get to the price somewhat higher over time, and we can get our costs down, then at some point they will meet, and we expect there to be a business opportunity. What you're looking at here is a mapping that we've done in Europe. We've developed a tool to map industrial sources. What you're looking at is about 350 industrial sites in Europe, each larger than 100,000 tons per annum. Many of them are obviously a lot more. And we've screened industries with potential. So you're looking at waste incineration, waste to energy, contributing somewhere in the 5 to 10% of the global CO2 emissions per year. Cement is a similar number. It's a huge CO2 emitter. We have biomass and biofuel, which is relevant in the context of negative emissions. We have refineries, steel, gas, hydrogen, electricity, fertilizer, data centers, and we've also started to talk with the suppliers of direct air capture facilities that essentially pull CO2 out of literally thin air. And there's let's say there's no shortage of CO2 sources. But how do you get from recognizing that there's a lot of sources to creating a business? We typically work in what we call funnels, and what you're looking at here to the right is our funnel with the 350 emitters that I talked about, representing more than 300 million tons per annum. We have then developed a framework. RFI stands for Request for Information. So we have a structured dialogue with some 60 companies representing a obviously smaller volume, it's a subset of 300. We have developed further into what we call non-disclosure agreements with 27 companies. And we have letter of intent or MOUs with some subset as well. So you can see the list of companies to the left there, relatively large industrial players in Europe, representing a number of these industries, hard to abate industries that exist around the globe. They are around Europe rather. We also now recently signed an MOU with Microsoft, who have publicly announced that they will get to zero emission and ultimately also mitigate their historical CO2 footprint from the inception of CO2 of Microsoft in the 70s. And we have a lot more which are not public yet, but there's a lot of interest. And of course, the idea is to get from a memorandum of understanding to binding agreements, heads of terms and service agreements. It's hard to see, but the final number here is, by coincidence, 5 million tons per annum, which is a conservative estimate of the capacity of the pipeline that we're building in phase one for Northern Lights. So it's our facility, as I said earlier, is built for 1.5 million, but we have pre-invested in some capacity. So we believe from that onshore facility that we can get north of 5 million tons per annum total capacity, with some extensions, meaning more pump capacity and some more wells offshore. So there are obviously some challenges related to building an industry, and we started out as a conventional oil and gas project executioners, where we, in the normal concept, have a known resource. We have a regulatory framework that exists. We have a business case, basically stating that there is value in selling these products, and there's an existing and predictable market. Typically, when we develop projects, we go through a project maturation funnel, starting with business identification, goes through early phases of project maturation. We have an investment decision, we go through execution and then operation. Of course, we invest in this phase, and we recover in the operations phase. And we typically have a relatively mature technical funnel. We have known or at least predictable risks. We freeze our concepts and typically are not schedule driven in at least planning of these normal oil and gas projects. When it comes to Northern Lights, it's much more interesting. Obviously, we have an unknown resource. We have this storage reservoir that we've identified, but we don't really know how much it can take, because we don't have the luxury of drilling a lot of very expensive appraisal wells. So there's a bit of, let's say, gambling in the total storage volume that we can expect in that area. We expect it to be several 100 million tons, but we have to be careful as prudent operators. So we've committed to 40 million tons total storage. And then when we get started with injection, we obviously expect to prove much more. But the whole resource validation is harder than we do in normal projects. We really don't have a good regulatory framework. There are some regulations, but it's not fully embedded into all the countries associated, and it's not really well tested. So we have a storage regulation in the European Union. We haven't really tested it a lot, so you can say the regulation are leading the industry in a way. If you think about conventional industrial buildup, it starts with an industry that gets regulated once you learn something. Here it's a bit the other way around. There is absolutely no business case initially, because the cost of doing this is much higher than the value of doing it. So we have to find the smart ways, and of course there's no normal markets. We are working to establish that, so that's why I showed you the funnel. There will be a market at some point, but it doesn't exist when we execute the project. And of course, the maturation part as a project executioner is somewhere where we have some known risks, but we have many, and I apologize for this not being a complete sentence. We have many risks that we have little experience in handling in terms of, in particular, the remnants here. And then we, of course, due to the fact that we had limited subsurface information, we froze our concept early before we had what we call subsurface validation. And we are schedule driven because we need to be ready to deliver on the CO2 injection by 2024. Another part, which is probably known to most of you, is that CO2 is lot different than hydrocarbons that we're used to. It forms dry ice if it's emitted from pressurized conditions through the triple point. This displaces air. It makes a lot of noise when emitted. It's cold. It doesn't burn, which is a good thing, but there's a lot of specialities with CO2. The picture you're looking at is from a test we just recently performed in our lab facilities in Porsgrunn with emitting CO2 to air. So you see sort of a cloud here, which is not CO2, but a mix of dry ice and mainly frozen or condensed water. So these are important things, and of course, most of you, I guess, familiar with the base curve for CO2, where we are typically operating in the liquid and supercritical area, but for maintenance and planned events need to go through to the atmospheric pressure, which goes through the triple point, which is an interesting challenge for technologists. And we obviously have developed a philosophy for this. We have no conventional flare system, for instance, which is something that we're used to on petrochemical plants. So there's no need for it, and we can't have it because of the dry ice formation. So there's a few special nuggets for designing CO2 plants. So I'll end the presentation by a couple of slides stating where we are. So this here is a very busy slide showing the process behind us. We have submitted a plan for development to the government. We have made an investment decision. We have had the project approved by the European Surveillance Authority. We have had the white paper approved in the government, and we've had budget allocated from the government. So the first part of this, what we call phase one, is as you then can deduct, supported by the Norwegian government. So that's part of the budget, and here is the Norwegian Oil and Energy Minister presenting the project. So we're out of the study phase, we're into execution, and of course the status is that we have entered into the majority of the execution contracts. We have started. We have a site office in operation, and we are going to start up CO2 injection mid-2024 according to plans aligned with Norcem. And the pictures show you the state of affairs where we are drilling and blasting rock and moving it out. So this is the pre-existing industrial area where there's some other industrial actors in operation. We have also formed a new company, so this will be run by a company called Northern Lights Joint Venture DA, which was formally established on the 5th of February, so very recent, and all the regulatory obstacles have been passed, predominantly linked to EU law on competitive clauses. So we're ready to go, and the company is now in its inception, forming, establishing office policies, etc. And we're going to transfer assets and ownership from the project into this company over time as we mature. So that concludes what I plan to say. So if there's any questions or discussion points, we can take that.
Thank you very much for this inspiring talk. I'm waiting for questions. So there is a question from Uni Osby that says, based on your current experience on CO2 storage, what is the purity requirements of CO2 for storage? And is it similar to what is required for use in food industry, or could small amounts of CO2, SOx, NOx, methane be tolerated?
Yeah, so the answer to that is that there are a number of considerations when it comes to CO2 purity. It's not as strict as in the food grade industry, but we are transporting CO2 in liquid form, and of course the contaminants, they impact the equilibrium state of CO2, so we don't want too much contaminants because our ships will be designed for a certain property. Then some of these components are dangerous to health, so we want to have, let's say, H2S at a low level, and some of them are a threat to the integrity of the facility. So we have tried to be very cost effective when it comes to the design of the facility. So for instance, we have a carbon steel pipeline which limits the amount of free water, limits the amount of oxygen, limits the amount of hydrogen that you can put in. So there are some relatively firm, strict limits to the composition. The composition you can find in the feed report that we have publicly made available. I'll put the web address in the chat later. The CO2 composition for the reservoir is, let's say, less strict. It has to do with the water and rock chemistry in the reservoir, but that's mainly regulated by the storage regulation, which says there should be overwhelmingly CO2 in the product stream. Which means you can't add the things to it, you have to take things out of it. So typically we have ppm level contaminants, meaning we have CO2 mix, which is 99-point-something% pure CO2.
Does that answer the question for Uni? Yes, thanks.
So if you have questions about the specific CO2 composition, you're welcome to go into that website and look up the feed report. It states what the CO2 composition is.
Okay, thank you very much. So the next question we have is from Adelbert Hude. You say CO2 is safely stored for long periods of time. Would you add some radioactive waste in the CO2 aquifer that would kill two birds with one stone?
Yeah, I'm sure it would. That's something that we have never thought about. So maybe it's a good research topic, but it's certainly not something that I'm prepared to say anything about at this point.
Yeah, it sounds a bit of a controversial topic. So then the next question from Harun Margerefte, which, by the way, we were looking before. What safety considerations are taken into account during the shipping, the ship loading in the event of CO2 leak at port?
Yeah, good question. So we have a system where, so fortunately, CO2 leaking from pressurized conditions are relatively visible, and you can also hear it because it makes a lot of noise and creates a lot of condensed water from the air. So detection primarily is by observation, but we obviously have gas detectors, we have evacuation routes, we have emergency procedures, we have breathing apparatus placed on strategic points in the facility to enable safe evacuation into the administration building that I showed you, which is a safe haven for evacuation. So in the unlikely case of a leak, there will be a shutdown of the facility, either automatically or manually by operators, and there will be evacuation back to the administration building, which is elevated with air intake ducts at the top of the building to avoid drawing the heavy CO2 into the building. So we're designing this according to industrial practice for petrochemical facilities with sort of the applicable modifications to the fact that CO2 is different than hydrocarbon.
Thanks. I think that answers the question. The next one comes from Mireille Feist, who is wondering what are the CO2 emissions per kilogram stored for this capture and storage pathway, and what are the main contributors to these emissions?
So, as I said earlier, we are the CO2 emissions per kilo is a function of the injection volume, because a lot of it comes from the construction phase. That means if we're successful in getting a high volume, then the unit emissions will drop a lot. In the operations phase, the main contribution is energy used for capture. It is energy used for transport in the ships mainly. As I said, we're using LNG for fuel initially. We contemplate going to zero emission fuels in the beginning. But the energy consumption from injection is virtually zero, because we're using hydroelectric power to run the injection pumps, which are low energy consumers anyway. So what we have calculated, or rather Gassnova, is a government body in Norway working on CCS, have concluded that we're in the area between 2 and 10% on a life cycle basis, 10% being the case where we only inject the 400,000 from Norcem and we get no more. So in operation, it's capture and sea transport. Life cycle basis, it's all the steel and construction emissions to establish the facilities. You can see it as an infrastructure project where you build the highway, and the specific cost of the highway is, of course, a function of how many cars you are able to put on the highway.
Okay, thanks. I do have a question, maybe a little bit related with some of the previous.
Yeah.
So are you, in general, are you also looking into maybe transitioning this concept to not too much storage, but also downstream utilization of the CO2? And then what would you say is the key elements that you have to consider? And I say this may be related to the question on the CO2 purity, but perhaps there are others, I don't know.
Yeah, so our project is an attempt to address the climate challenge. So it's driven out of the Paris Agreement, and we see utilization not as a sort of a very important viable path for addressing climate change, because the volumes of utilization are small. Where the ambition is to store gigatons of CO2, and utilization is a relatively small part. So we welcome all utilization projects, but it's not something that we focus on in Northern Lights. Of course, when we have CO2 that can be sold to a utilizer, that's not really part of our business model.
But perhaps, I mean, I agree that the scales at the moment are not really matching, but in a sort of long term, perhaps it also affects this business model that you are now describing, because right now it's mostly based on, let's say, penalties on CO2 emissions, but when that changes, then the whole business model is sort of gone, or So when there are no problems, then there is no incentive then.
So we're simple people working in publicly listed companies with a relatively short focus. So obviously we are aware of the long-term, let's say, scenarios. We are aware of all the good initiatives going on in utilization of carbon, but it's not something that we as a project team focus on. So the individual owner companies in Northern Lights are to various degrees interested in the utilization of CO2, but it's really not part of scope for the Northern Lights joint venture. That is purely transport and storage of CO2 to aid the climate challenge.
Okay, clear. Thanks. There is another question by Raf Rouland. At which pressure level is CO2 transported to and injected into the well?
Good question. The transport conditions are typically 15 bar pressure minus 26 degrees. It varies a little bit. Our design basis for transport is 13 to 18 bar. And when we store them in our tanks, there's a big pressure difference between the top of the tank and the bottom. These tanks are 30 meters tall, but that's typically the transport conditions. We inject at the pressure required to move the CO2 into the rock, which is a rate-driven number. We are hydrostatic, so in theory, with the CO2 being almost the same as water in the injection conditions, we only have to push it. So we're starting out with in phase one, the injection pressure from the onshore facility is somewhere in the range between 45 and 100 bar, depending on rate. And the design pressure of the pipeline is near 300 bars, which is the expected pressure when we utilize the max capacity of the pipeline, being somewhere north of 5 million tons. But we stay above 45 bar to ensure that we are always in the single phase in the pipeline. And so that at low injection rates, we will control the pressure by choking at the wellhead. And when we have 1.5 million, the expected operation pressure is somewhere in the range of 80 to 90 bar.
Perfect. Thanks for this elaborate answer. Well, is there any more questions from the audience? We are reaching the end, but there are a few more minutes if there are more urgent questions. It doesn't look like that. Then I thank you very much to all the speakers for the nice presentations, and also, of course, to this plenary presentation. Before we finish, I just want to very quickly share one slide that I made a mistake before. So that was about the project of Converge. Oh. And I put the old version of the presentation. So now you see also including the acknowledgement to the EU funding and of course all the projects. So apology for that mistake. And now we have time, as you know, from 11 to 11:45. There's time for the posted session, as well as a break if you want to have it. The dynamic is similar than yesterday. You are supposed to see the posters online and then connect only to discuss with the presenters. And there are parallel channels already. So for those who were here yesterday, you are already familiar. And then at 11:45, we continue with the parallel sessions. So thanks again and see you later. Bye. Oh, yeah, sorry. Well, there is a very short, yeah. So I have a comment from Harun Again, I cannot pronounce your surname. I will go to your slide. This is a coordinator from T4U. So let me, which was that one? Number 8.
That's it. Right. One more down.
No, this was, yeah, this one.
So, yeah.
Yeah. Yes, you were not here before. Sorry, I jumped you. Yeah, so we have now a very short time, a few minutes, if you could introduce yourself.
Thank you very much. And I'm sorry there was a mix-up, it seems like this morning, but so just very quickly, one of the projects which is participating in this call for this international conference is the C4U project. We started on the 1st of April last year, and it's a 4-year project. We're basically looking at 2 technologies, capture technologies for capturing CO2 from the steel industry. We are going through the entire chain, which involves several work packages. The first work package is basically to raise the level of these 2 capture technologies, novel capture technologies, to TRL 7. Once we've done that, it's basically to integrate these 2 technologies into a real industrial plant. In this case, we have ArcelorMittal, which is one of the largest CO2 emission industries in the North Seaport area. Once we've established that, then we go on and we look at integration into an industrial cluster, basically by looking at not only the connection of the capture of the CO2 into this cluster, but also the way that the industrial cluster, that the flow within the pipeline infrastructure for ultimate storage into the storage site also is impacted by integration of these 2 capture technologies, along with several other emitters. The last work package deals with the societal readiness, much like many of the other projects, to make sure that the concepts that we are applying and the in the public perception as far as the integration of these technologies into industrial cluster is favorable. Of course, this is not a money-making business, so we need to make sure that they have the right business models to ensure that there is financial incentives for basically rollout of such industrial clusters in the North Sea. So my apologies again. I did this in quite a rush, but you have our website is given here. As I said, we started about 8 months ago, so we are at the beginning of the project, and we very much hope to collaborate with the other participants in this international call who are doing similar work to us. Thank you very much.
Thank you, Arun, and again, thank you everyone, and I hope you now enjoy the poster sessions and the break.